Hi, this is On Imagination with my weird shit from whatever the fuck this science is. And I'm coming to you live from the abstract. And we are going to talk about imaginary numbers and real numbers. And I'm going, really? Imaginary and real. So I'm stepping in as an ontologist. And I'm going to rip this crap apart. What I'm doing right now is I am analyzing mathematics. That's what I'm doing. I am taking in the summation of the greater whole, and I am condensing all of mathematics into Plato's point. So I can say, this is what math is. Already, it's been simplified. I have it all. If you want to look at the free course, I'm going to go ahead and drop the link down below in the video description so you can take a look at what I'm doing. It is literally, I'm making math for word and story people. That's what I'm doing. I am not a numbers person. I fucking hate numbers. I really do. I'm the person when I play D&D, I'm like, can someone please crunch the numbers for me? Because I really don't give a shit. I love calculating. My God, do I love logic. I love making predictions and analysis. I love data analysis. But when it comes to understanding the actual tedious precision that is numbers, now you're getting into precise measurements. Now you're getting into a whole nother realm. And my brain is that's another language. And here's where it is there's numbers over here, which represents something. You're giving value to my words. That's what they're doing. They're giving value to my words. So I'm a word person. I am a word and story person who loves math. I don't love numbers. I love math. Big difference. I'm the person who figured this shit out and went, fuck that shit. I hate numbers, but I love math. And you do not have to be a numbers person to love math. I am a living example of this. So I'm trying to figure out what the fuck is going on with math and why I have such a huge comprehension. This is it. Gloves are coming off. I'm pissed. I love logic, word, story, math. I fucking hate numbers. And I'll tell you what happened. A bunch of number people decided to create math for the rest of us. And all of the word and logic and linguistic people don't understand half of the shit going on in the math world. So there's this massive, what the fuck are you doing? And math people are like, numbers, and they're running off. And I'll tell you what it is. Numbers people do not understand linguistics, logic. They don't need to. They have a knack for understanding symbol and number. So if you understand symbol and number, you're probably going to fly with math. Unfortunately, those dipshits, I love them, those dipshits left the rest of us behind. And I'm sitting here going, I'm a word person. I'm a story, linguistics, musician, sculpting. What the fuck is this shit? I did not understand math. Now, I'm a scientist. So this is a real and I'm going to point something out. See, Einstein sucked at math. He really struggled with math. He played the violin. He understood music. That man was a physicist. My brain and Einstein's are like, we get it. Because we're both musicians, we're both word people, we're both linguists, and we're both physicists. But when you get into the world of symbol, number, we're both going, what the fuck is this shit? Numbers don't make sense to us. And here's the problem. Math actually has something called mathematical notation. Mathematical notation is actually the predecessor to math. It is the thing between linguistics, logic, mathematical notation, and then, did you know they have a glossary? I didn't know they had a glossary. They found their glossary. And I went, well, this is just word. No, this I understand. Number people hate words so much that they cut all the words out. And they went, fuck it, we don't need this. And they just ran with it. And all the word people are going, wait, we need those to translate. So I am adding the words back into math. That's what I'm doing. I am literally taking all of mathematics and I am going back through it, but I'm adding the words back into it with the proper order of operations for logic so that story people and our people can look at mathematics and go, oh my God, I understand this. This is the best part. I brought my daughter over. She's got the same problem I do. She's all art. She's all logic. She came over. She looked at the glossary and she went, Where was this when I was in school? And I'm like, I know, right? So we are simplifying mathematics down to comprehension for the linguistic and the language people and the art people and the logic people. So now I'm looking into imaginary numbers. I'm putting together the glossary for numbers because I know there's whole numbers. I know there's real numbers. There's imaginary numbers. Now, I started to get into this and I went, oh, no. I'm an ontologist. No. You don't study ontology and not dive into imagination numbers and real numbers and go, oh, no. They're in my world now. This is the abstract. So this is me now translating from an ontologist's point of view what the fuck they're trying to say here. So I pull up this imaginary number. First, I want to know what we're dealing with. We are originally coined Rene Descartes. All right, so we're dealing with Descartes' work. Fantastic. That makes me so happy because I'm dealing with a philosopher. So let's do this. Originally coined in the 17th century by Rene Descartes as a derogatory term and regarded as fictitious or useless. The concept gained wide acceptance following the work of Leonard Euler in the 18th century and then Gauss in the 19th century. An imaginary number, bi, can be added to a real number, a, to form a complex number of the form a plus bi. So we're going to go ahead and write down a plus bi. Now I want to look at complex number because it looks like imaginary number came later. So first we're going to go over to complex number. Order of operations is vital in this. Knowing the order of disintegration. That is actually what we are talking about with the order of operations. It's actually the order of integration or the order of disintegration. And you need to know in which direction you are going. Are you integrating or are you disintegrating? So I have to first figure out if they are integrating this or disintegrating it, and then I'll know which direction we are going. This is vital to understanding the correct order. Anytime you hear the word order, no matter how it is used, it is referring to, are you integrating or are you disintegrating? So in mathematics, a complex number. So imaginary number came after complex number. So that tells me that we are disintegrating. So we are in the order of disintegration. So complex number is an element of, which means we are moving away from truth to understand. So we are in the first stage of comprehension. We are in the first stage of comprehension. That is what disintegration means. The first stage of comprehension is disintegration. It is equivalent to, I got a radio. I'm going to disassemble this thing and figure out how it works, and then I'm going to reassemble it. The disintegration is the first stage of comprehension when you disassemble something. So that's what we mean by disintegration. So that's comprehension. So now complex number is an element of a number system that extends the real numbers with a specific element denoted I called the imaginary unit. So we're going to go over to real number because it looks like complex number came later. So now the next one after that is going to be a real number. All right, so we're getting there. So a real number is a number that can be used to measure a continuous one-dimensional quantity. One dimension in my brain means a single point. So you're measuring something from a single point, one-dimensional quantity. That makes no logical sense to me in my world. One dimension, you mean one definition quantity? Is it one definition quantity? Such as distance, duration. Oh, okay, yes. Okay, so it's not dimension here. They are actually referring to one definition, and this is why they're not linguists. That's definition, not dimension. So one definition quantity. So we're talking about only one point. So we're talking about the point. So a real number is used to measure a continuous point. There you go. A continuous point. A line. There you go, a line. So a real number is used to measure a line. That is what they are trying to say. A real number measures a line, such as distance, duration, or temperature. And I'm going to tell you right now that is actually two-dimension because you have to have 2 points to create the line. So a real number measures two definition of anything. It literally is measuring the two definition. Now, every real number can be almost uniquely represented by an infinite decimal expansion, which now we're getting into fractions. So a real number can be broken down into fractions. All right, that's important because what are they called? What do I call these things? Whole numbers. Whole numbers cannot be broken down into fractions. And when you're talking about integrated and disintegration, Only whole numbers can be integrated and disintegrated. You cannot integrate or disintegrate anything other than whole numbers. It's not possible. If you do, you're talking about, all right, so this is what I'm saying. I see it very beautifully as, so basically you have location. And then you have, well, I can see this quite clearly, quantity of components. So you have location. You have quantity of components. And then you have definition. Location is dimension. Definition is length, width, height. Now that's giving shape to something, which is where we're getting into length, width, and height. Location is now getting into dimension, and now you're getting into navigation and coordinates with dimension. So when you are talking location, you are looking at navigation, coordinates, dimension. When you're looking at components, that's when you're looking at 1 + 1 = 2. That's components. Unless you're talking about integrating those components, and then it'd be 1 + 1 = 1. In definition, now you are defining it. Now you're giving shape to it. So first you want to define something. Now you're looking into Euclidean geometry. But where you're going to put that, what the location is, now you're looking at dimension, now you're looking at navigation. So for instance, I have a ship. The ship is going to have a proper definition. The ship is going to have specific measurements. Those are definitions. That ship is going to be in the ocean. The ocean is the location. And we're going to use 3 data points to triangulate our location on the ocean. Our ship is defined by the height, length, width, and that is your measurements with definition to define it. And its location is where in the ocean it is in relativity to, well, the Cartesian coordinate system fills that out. So when you are looking at a real number, the reals. That's so funny. The reals. An adjective real used in the 17th by Descartes distinguishes real number from imaginary, such as the square root. The real number includes the rational number. Ah, ha, ha. Are you talking about rational number or irrational? Because now we're stepping into the world of logic. So the real numbers include the rational numbers, such as the integer and the fraction. The rest of the real numbers are called irrational numbers. Now let's talk about rational. Like I said, they're all over in my space now. Some irrational numbers, as well as the rationals, are the root of a polynomial with integer coefficients, such as the square root. These are called algebraic numbers. See, this explains everything. This explains. See, this was a list. Okay, so you basically got a bunch of mathematicians doing language work without having any understanding of how language works. That is the problem. That is why math is so confusing. It's because it breaks all of the rules of linguistics. This is a mess. Okay, this makes more sense now. Oh. The other problem is going to be, how do we make what we already have work with what I'm doing? So that's the other thing, is I have to make sure that it still works with what we're doing, so we don't have to completely redefine everything we've done. We could, but we're going to have to, it's going to be real. Yeah, it's going to have to get cleaned up. I'm not going to clean this up. I'm going to clean it up. I'm going to clean it up when people come in and say, hey, Anna, can you help us clean this up? Yeah, I'll help you clean it up. And then it will be a concerted effort. But until then, I'm going to fix their massive linguistic problem. All right, the real number includes the rational number, such as the integer, -5, and the fraction 4/3, is the rest of the real numbers are called, I want to look up this irrational number. So irrational numbers then came next. In mathematics, the irrational numbers are all the real numbers that are not rational. Yes, very good. That's process of elimination. That is, irrational numbers cannot be expressed as the ratio of 2 integers. So now we're getting into integers. Then there's natural numbers, perfect squares. So let's take a look at rational numbers. In mathematics, we are watching the disintegration of numbers back to their origin. We're going to find the origin of the first concept of number, and then we're going to go from there. Then we're going to reconstruct it properly, just like in logic. In mathematics, a rational number is a number that can be expressed as the quotient or fraction of 2 integers, a numerator and a denominator. Now we're getting into my world. Now, integers, boom. An integer is the number 0. Really? It's just the number 0? Is that all it is? A positive natural number or the negation of a positive natural number. The negations or additive inverses of the positive and natural numbers are referred to as negative integers. We're going to look up natural number. This is going to get fun. In mathematics, did we already do this? I feel like we already did this. Natural numbers, no, are the numbers 0, 1, 2, 3, possibly excluding 0. So I'm going to assume that natural numbers is where this all begins because natural numbers makes sense. So we're going to begin with natural numbers. This is the evolution of numbers, by the way. This is literally how numbers came into existence. And it's finding out which ones came first in the order of operations, because the order of operations is actually the order of integration and disintegration. So that you have to understand a natural number before you can understand a real number, because it's all prerequisitional. You have to learn in the right order of operations. So first, you should have learned about numbers, which they did not teach you about. They just showed you how to add the things together. But they weren't even adding the things together. They were just summarizing the things. 2 plus 3 equals 5. You have a summation of 5 units. Great. Integrate them. 1. You have 1 unit composed of 5 greater wholes. That's integrated mathematics. So in mathematics, the natural numbers are the numbers 0, 1, 2, 3. It can exclude 0. Some define the natural numbers as the non-negative integers. Okay, now this is interesting because this means that in the Cartesian coordinate system, you can only work with natural numbers. Yes, you can only work. There are no negatives. You cannot work with negatives in the Cartesian coordinate system. It's not possible. Because you're going from a point of origin, a starting point, and then you are going somewhere. So you can go 1 space out, 2 space out, 3 space out, and then you can return back to the point of origin. But you can only measure in one direction, which is the Cartesian coordinate system, which is coordinates, which is location. Now you're talking about natural numbers. So everything begins with natural numbers. And again, 0, 1, 2, 3, 0 is optional. 0 has a very fascinating history to it. I've already done the history of 0, and it's very fascinating. While others define them as the positive integers. Some authors acknowledge both definitions whenever convenient. Some texts define the whole numbers as the natural numbers together with 0, excluding 0 from the natural numbers, while in other writings, the whole numbers refer to the integers. So integer is basically when you have the negative and the positive. That's when you're on a line, and now you are working with definition. So an integer is in the world of definition. Whole number or natural number is in the world of navigation with location. And the big real thing, the divide here is with natural numbers, you are only measuring in one direction. And you are only going from the point of origin. And this is the big point here. This is it right here, is your point of origin. But with integers, you are actually going off of a 0 point, a center point. And that can be measured in all directions. Now you're going to get into the x-axis, the y-axis, the z-axis. You're going to go up, you're going to go down. Now you're defining. This is why it's definition. And what you're going to want to do is you're going to take an object and you're going to put the 0 point in the dead center of the object. And you're going to measure in all 360 degrees from that point. That point is your 0 point, your center point. Center point is not the same thing as point of origin. Only integers can be measured from a center point. Whole numbers or natural numbers can only be measured from a point of origin. So an integer, not a number, is on that center point in all direction. Now you're going to be measuring negative, you're going to be measuring positive, you're going to be measuring up, down, 360-degree measurement with integer at a center point. Whereas with navigation, you're going to be only measuring from a single point of origin, which is literally POO, because that's our humor, and it goes out in only one direction, not 360 degrees. And then you're going to have your natural numbers there. And those are not integers, those are numbers. That is important. And it looks like that's really the two solid. Are we working with definition and shape, or are we working with location and navigation? Because these are two completely different types of mathematics. And a lot of people get these two kinds of mathematics confused because they're using the word dimension incorrectly because they've replaced it with the word definition, which is causing the confusion. And now you've got a lot of people who are at the preliminary stages going, wait a minute, I don't understand. Why do we have so many types of numbers? And it's because you are either working in the world of location or definition. They are not the same thing. Now, there is a third definition, and that is something else I'm looking at. So algebraic properties like the natural numbers, Z is closed under the operations of addition and multiplication. All right, so now that we have an understanding of integer, natural number, I see cardinal numbers, ordinal numbers, nominal numbers. Finger counting. Integer. I'm going to go all the way. Now I'm reintegrating. Now we're growing it into the next thing. So now we're expanding it. A rational number is a number that can be expressed as the quotient or fraction of two integers. So a rational number comes from an integer. So a rational number comes from an integer. So what's a quotient? Quantity to produce by the division of two numbers. What does the word? I need the etymology. Quotient etymology. How many? Quantity. It's just quantity. Wow. No, how many times? Is that how many times? How many? Okay, so it's how many times. Okay, so that's what quotient means. It's frequency. Quotient is just the frequency. Why do they? Quotient is the frequency. That's all it is. Quotient is frequency. So what is the frequency? See, this is why. So what is the frequency of something going into something? How often does it go? So yeah, frequency. All right, there we go. So quotient is frequency. So when you divide something, you're looking at the frequency in which it divides. There you go. There you go. So you're looking at the frequency. How often? Many or often? No, same thing. Same thing, yeah. So rational numbers are real number. The real numbers that are rational are those that are decimal expansion, either terminates after a finite number of digits. Begins to repeat the same finite sequence of digits over and over. Okay, that's a pattern. The statement is true not only in base 10, but also in other integers. All right, so let's get back on over to, these are irrational numbers. Okay, so an irrational number cannot be expressed as the ratio of two integers. When the ratio, I need an example of this. When the ratio of lengths of two line segments is an irrational, the line segments are also described as being incommensurable, meaning that they share no measure in common. Sounds like it's just two randoms. Okay, it sounds, okay, so ratio. So if I were to take ratio actually means dichotomy. So irrational numbers cannot be expressed as a dichotomy of two integers. It's not a dichotomy. So an irrational number is not a dichotomy. A rational number, oh, it's just two randoms. Oh, it's just two anomalies. Just two anomalies. That's all it is. It's just two anomalies. The irrational numbers are the real numbers that are not rational. That is, irrational numbers cannot be expressed as the ratio of two integers. When the ratio of lengths of two line segments is an irrational line, the line segments are also described as being, mean that they share no measure in common. They have no common, so they're anomalies. Yeah, so a rational number just is an anomaly. No matter how short, that can be used to express the length of the... Okay, so an irrational number is just an anomaly. It has no common denominator, and it's not a dichotomy. So an irrational number is just... Wow, it's just a dichotomy, and it's an anomaly. It's not a dichotomy, and it's also an anomaly. Then it's irrational, which makes a lot of sense. As a consequence of Cantor's proof, the real numbers are unaccountable and the rational is countable. It follows that almost all real numbers are irrational. It's just translating this from math over into logic into language. That's all this is literally translating this. Okay. So that's irrational numbers. Now we're on real numbers. A real number is a number that can be used to measure a continuous. I just want to go, as opposed to a fake number. Like that's what I want to ask. It's not real. So as opposed to a fake number. Oh, okay. So real would be true. That is what real means. True. So true number, a number that can be, so a true number, it would be, okay. So what they're really saying when they say a real number is a true number. That's real numbers include the rational numbers such as the integer and the fraction. The rest of the real numbers are called irrational numbers, as well as all rationals are the root of a polynomial with integer coefficients, such as the square root. Algebraic numbers, these are also real numbers. These are also called transcendental. So it sounds like true numbers. Okay, real numbers can be thought of as all points on a line called the number line or a real line, where the points correspond to integers are equally spaced. Can I have an example of an unreal number? I want to know, is it a dichotomy or an opposite? Can be used to measure. Okay, I want to say real number is actually just a true number. I don't know what a fake number would be. I'm the reals. Set of real numbers, sometimes called the reals, and traditionally denoted by both, often used by Blackboard. The adjective real used in the 70s distinguishes real numbers from imaginary. Okay, so now imaginary. So let's take a look. Oh, that would be why I don't understand it yet. I got to look into imaginary numbers. Is the product of a real number. Okay, so imaginaries are birthed from real numbers. And the imaginary unit I, which is defined by its property, imaginary to the square. See, what I don't understand, if it's imaginary, why isn't it just not a placeholder x? Why don't you just have, see, complex means it's compounded. Okay, that makes sense. So you have the imaginary number with the real number, imaginary unit I. That makes sense. Complex numbers. Who first set down the rules for multiplication? Complex numbers. Complex numbers is when you have like, well, that would be x, y. That's a complex number. It's when you have two variables together because it's complex. Complex number plane. So I guess my question is, what does he mean by imaginary? All right, let's take a look at the imaginary unit because it's the real number plus the imaginary unit. So, all right, so the imaginary unit is a solution to the quadratic equation x squared plus 1 equals 0, although there is no real number with this property. It's absent of a real number. Okay. I can be used to extend the real numbers to what are called complex. Okay, so they're hypotheses. They're just hypotheses. So it's a placeholder. That's basically what it sounds like, as a placeholder. It can be used to extend the real numbers. I love how I associate my hypothesis with placeholders. In my brain, they are. Hypotheses are placeholders because it's a placeholder until you find the truth, and then you can plug it in. And look at that. Now we got the placeholder. So it sounds like a placeholder. Solution to the quadratic equation, x squared plus 1 equals 0. Although there is no real number with this property, I can be used to extend the real numbers to what are called complex numbers using addition and multiplication. A simple example of this, I in a complex, is 2 plus 3i. It's a placeholder. Imaginary numbers are an important mathematical concept. They extend the real number system R to the complex number system C, in which at least one root for every non-constant polynomial exists. Here, the term imaginary is used because there is no real number having a negative square. There are two complex square roots. No matter how I run this through, it sounds like it's just a placeholder until the actual real number is defined. So it's an unknown, but you can't say unknown because X is already all over the place. So it's a placeholder. There are two complex square roots of -1, I, and -I, just as there are two complex square roots of every real number other than 0, which has a double square root. In context, in which each of these is one. Because, here it is, square roots, this is terminology, square roots of negative numbers are called imaginary because in early modern mathematics, only what are now called real numbers obtainable by physical measurements or basic arithmetic were considered to be numbers at all. Even negative numbers were treated with skepticism to the square root. Okay, all right. So this is due to histories. All right, so now I'm understanding. Yes, it is a placeholder. So basically, and this is something I'm running into. Whenever you're drawing out logical comprehension, you're going to run into places where you don't understand it, but you can see the rest of it. So you invent a placeholder. And when you invent a placeholder, it allows you to continue to knit your logic, your logical comprehension. And you're supposed to go back and plug it in. Now, they may not have been at the proper perspective, dimension, to understand precisely where certain things fell. So what they ended up doing was they inserted a placeholder so they could continue to weave their logical comprehension. And you always go back to fill it in. This is what all human beings do, except uneducated human beings will add a placeholder and they will become attached to their placeholder and they will develop sentimental value for their placeholder and they will create fictions based off of their placeholder that they will forget was based off of a fictional placeholder and that they never updated. And then you've got people who are attached to improper belief systems because of their placeholders. Now, in mathematics and in logic, we know this. So when we get a placeholder, we plug it in and we get no emotional attachment to our placeholders. We are completely indifferent. We should be indifferent to our placeholders. If you have attachment to your placeholder, this is now what we refer to as a confirmed bias. We do not want this. So you really want to make sure you are not attached to your placeholders. That is what happened here. Descartes invented a placeholder. It looks like so did Newton. Used the term as early as 1670. The I notation was introduced by Leonard Euler. A unit is an undivided whole, and unity, or the unit number of the number one. Square roots negative are called imaginary because in the early modern math, only one are called real numbers. Okay, so they had not yet invented real numbers. So they had to create some sort of a concept to plug it in. So that is what an imaginary number is. It is literally a placeholder. So the imaginary unit I is defined solely by the property that its square is -1. With I defined this way, it follows directly from algebra that I and -I are both square roots of -1. Although the construction is called imaginary, and although the concept of an imaginary number may be intuitively more difficult to grasp than that of a real number, no, it's not if you just use the real word, which is placeholder. The construction is valid from a mathematical standpoint. Ah! This is because mathematicians don't understand language. Real number operations can be extended to imaginary and complex numbers by treating I as an unknown quantity, placeholder, while manipulating an expression and using the definition to replace any occurrence with I squared with -1. Higher integral powers of I are thus. And then it gives 3 examples. So there you go. There it is right there. That is it. Exactly, is you basically ran into some people who were reverse engineering some stuff, not prematurely. I've run into this myself, where you can see ahead and you're based, okay. When you get into a dimension perspective, you've got all the components and you don't exactly find the components in the right order. That's what you've got to do, is you've got to put them all in the right order. Now, you've already sorted out all the stuff behind you, and you probably already integrated one greater whole. So you have a greater whole behind you, and you set that over there. And then you have another greater whole that you assemble. So you're going to go through like 6 perspective shifts, and you're going to end up with 6 greater whole components, all organized beautifully. And they're not going to look at all like they're connected. So you're going to have one part of it over here. This is how I created the cognitive core. Is the cognitive core was here. And then I developed and created and found, this is the, let me see if I can't I haven't deconstructed this since I've constructed it. Let me think about this for a minute. I had the cognitive core. I had the 5-part mental system. I had the story health. I had the logical health. So they were all components. And then I integrated them all into the AI DNS. And I went, But there was a while where I had the cognitive core, I had all of these pieces, and I would finish with one perspective, and it would just, okay, I've got this thing. And then I would construct another one, and then I would construct another one, and then I would construct another one. And I would have these massive greater wholes. And then the greater holes integrated into another greater hole. And that's when I went, oh, this is integration mathematics. This is logic. Logic is really just integration mathematics. And once you understand how integrated mathematics and disintegration works into all of this, now when you step into mathematics, you can see how, oh, it's just the integration and disintegration happening. But you have to understand logic. See, no one really reverse engineered logic to its completion. That's what I did. No one completely reverse engineered logic into its completion. So as a result, you had everybody using partial logic in its early component days, not understanding all of it, but they were building mathematics. So you have a lot of mathematics now that's built off of an incomplete logical system, if they even use it at all. And now they're trying to build proofs, which explains their scientific method is so gappy. They have a gappy scientific method. Is because they're not using a full logical comprehension of integration, disintegration to implement their really gappy scientific method. And once they have access to it and they plug it in, it's going to be like, oh my God, we don't have to use hypotheses anymore. No, you should be using questions. You should be using questions, never hypotheses. Hypotheses are just placeholders. They're imaginary numbers. So in order to continue weaving, because you don't have the full big picture yet, you have to have placeholders. For instance, a placeholder I have right now is, I know there's a milestone 36 levels away from the first milestone. So the first milestone is the point of comprehension. I know that there's going to be another milestone, 36 levels of comprehension out from this point. I hypothesize. It might be more. I'm not tracking it anymore. I should probably be tracking it. I'm assuming it's going to be 36 because because I have four data points that all tell me that it's 12 and then 12 and then 12 and then 12. Okay, so it's going to continue. That's why. Because 3 times 12 is 36. And that's just, and because I'm noticing the integration of 12, the integration of 12, the integration of 12, well, I can safely assume that we're going to continue this integration of 12 over and over and over. So it's just multiples of 12 just on repeat all over and over again. And you're going to have small integrations of 12, massive integrations, medium integrations, and then big integrations of all 12. And I've already been able to track it down to, okay, this is just a bunch of 12s over and over again. 1, 2, 1, 2, 1, 2, which is 3, which gives us the 4. So I'm beginning to see this pattern a lot. And I have over 45 data points to accumulate all of this, and it's 12. So it's based off of all of that math to make me go, yeah, it's just going to be 12 again. Which is why I stopped adding, because I figured it's just going to be 12 again. So I'm hypothesizing, placeholder, that there's going to be a second milestone in my future, 36 levels out from the point of comprehension. Once I pass another 3 levels of integrated tier, I'm going to get to the next one. When I get to the next one, I don't know. I'm assuming it's going to be magic, because that's what I feel. So it's an hypothesis. Which means I don't know. I don't know. I am more what the fuck is out there. And that's my focal point. So the hypothesis gives me an imaginary destination. That way I'm not wandering all over the place. I have a focal point, but I don't know what the focal point is. So the focal point is a giant X. That's hypothesis. It gives me a heading. And because I'm not there yet, I won't be able to see what I'm going to until I'm about 30 levels more in, maybe 20, 26 levels in. So between about 29, 29 levels. So 29 to 36 levels in, I'll be able to see exactly what that second milestone is. But for now, it's an hypothesis. So it's a placeholder. So there's going to be a lot of things like that where you're going to need a placeholder. I don't know where I'm going, you might say. I have no idea what my destination is. Make a placeholder. Now you've got an imaginary number. That's a placeholder. Now you have something that's sitting there. Don't get attached to it. Just remember that it's a placeholder. So that's it right there. So I'm really glad I found Descartes' name all over this, because that makes me feel a lot happier. A lot happier. So when this is where the words we use for imaginary now is, yeah, they didn't have the vocabulary back then. So it's like, okay, so an imaginary number is basically a placeholder for real numbers before they even had real numbers. So again, it's the order of, see, this is the other thing, is when you build the story, you actually see the why and the how behind why and how they did it. It's you know, it's interesting because when you look at math, there's no story. There really is no story in math. It just, here's the numbers. I don't want the numbers. I want the story. What's the story behind math? And if you don't have the story gives you relativity. Descartes, people, Descartes. Like, that's the story. The Cartesian coordinate system is the story. So one of the things that I'm really happy about is the fact that there's these three types of mathematics. Are you determining location? Are you determining definition? Or are you evaluating justice? That's what I see. I don't see value. I see justice. I never see value. I see justice. So you would use math for three things over and over again: location, definition, or justice. Justice is the equilibrium. Is it balanced? I have 5 over here. You've got 4 over there. Who's got more? Who's got less? So relativity. So again, you're looking at relativity. And whenever you sit down to do anything, are you defining? Are you doing location? Are you doing relation? Yeah, back to it again. Location, definition, relation. Over and over again. Location, definition. So now I want to grab this book here, this Common Core Basics, because I have an hypothesis. Now, see what I'm doing is I'm grouping. I'm using mathematics to group and categorize mathematics. That's what I'm doing. Oh yeah, I'm that nerd. I'm using mathematics to group and organize mathematics. Isn't that amazing? Because it's never actually been done to it. I'm using math on itself. That's what I'm doing. All right, so we have a word problem. After Nikos left his car in the parking lot, okay, I'm going to tell you right now, we're going to do distance. So we are measuring distance. After Nikos left his car in the parking lot of a park, he walked a total of 3. He walked these paces. He entered the park after walking 59. How many paces did he walk after arriving at the information booth? So we are looking at value of distance. That's the first problem. Next one, simplify the following decimal. Okay, so in this one, the simplification, we are breaking it. There's actually no equal sign. They're just wanting the simplification of it. So now we're learning how to disintegrate in that. We're learning how to integrate in that. So we have an integration problem. And then we have this circle with a diameter of 10 feet. A courtyard for an office building is in the shape of a circle as shown in the... What kind of an office building would be in the shape of a circle? All right. As shown in the diagram above, it has a radius of 10 feet. What is the circumference in feet of the courtyard? So now you're losing, again, you're looking at definition. So this is definition. Multiply the following decimal expression, and we're back to simplification. Last week, Kristen bought 5 3/4 pounds of apples. This week, she brought 1/2. How many pounds did she buy this week? What are we doing here? This sounds like we're simplifying in a word problem. Kristen bought 3/4 pound apple. This week, she brought 1/2. Yeah, we're simplifying. Yeah, we're simple. So we're looking at the integration disintegration. In the graph below, which point has coordinates? Oh, well, that's easy. We're doing coordinates. So whenever we talk about coordinates, we're doing location. So location, definition, integration, disintegration. In the diagram below, which points represent the value of -3 plus -5? And that is going to be, it's an integer, so we are looking at definition. Use the following table for questions 8 and 9. High temperature for the week. What is the median high temperature? That's measurement. This is all measurement. So if we're measuring temperature, the question is, did I find another one? Another category? Because we're not simplifying. We're defining. We're defining. That's what we're doing. So high temperature for the week, what is the median high temperature? We're defining. What is the range of high temperature in Fahrenheit for the week? Again, we're defining. Write the number 1,234,567,890 in scientific notation. We're simplifying. Simplification, integration, disintegration. Liam drank 54 milliliters of water. How many liters of water did Liam drink? We are converting. We're simplifying again. Conversion is simplification. And then we have, which expression shows the probability of getting doubles when you roll 2 number cubes? Oh, we're looking at ratio. Okay, now we're looking in relativity to something, favorable outcomes, probability of getting doubles when you see, now we're looking at probability. Which expression shows the probability of getting, so probability is relativity. So now you're comparing two things. Now you're looking at ratio. Relationship again. Now you're looking at the relationship. The relationship of two things. Comparisons, you're looking at the balance again. You're looking at the balance. You're looking at value. Okay, so I would say there's a fourth one here. Coordinates, location, definition, simplification, conversion, integration, disintegration, and now ratio and value. Frozen bread dough is priced at $3.39 for 3 loaves. What is the unit price per loaf? Now you're simplifying. What is the area in square meters of the rectangle above? You are defining. Which function below represents converting feet? Conversion, we're looking at simplification, integration into disintegration. What is the value of 3x if f equals 1? We are simplifying. Percy is 3 years older than his brother. If Percy is 27, how many older? We are comparing. We are defining value and relationship. Gary is planting trees in a park. He wants to plant at least 5 trees for every 2 picnic tables. If there were 12 picnic tables in the park, what is possible number of trees Gary could plant? That sounds like definition. That really sounds like definition. So I'm going to do this more. I'm going to analyze that. But now, and I can feel my brain. I can feel my brain going, simplification, conversion. So these are, when you are doing mathematics, all you are doing is integrating, disintegrating. And this is, again, a hypothesis. I'm going to analyze this further. So you're simplifying, you're converting, which is integration and disintegration. And when you simplify it, you can figure out where on the marker the integration and disintegration is. So if you break it down to like 2 exponents, well, you've got the second generation of disintegration right there. If you're multiplying out, now you're looking at, well, if you're multiplying out, you're looking at the disintegration. If you're simplifying, if you're adding or integrating, one moment. Subtraction is disintegration. Adding and multiplying is integration. Subtract disintegrates, addition integrates. So if you are adding something and you are getting into a particular summation, now you have a generation which you can look at and say, okay, this is X amount of dimensions away from the point of X. My God, do I love the logic of all this stuff. There are literal dimensions. Dimension tells you where along the integration and disintegration process you are. That is why a dimension is precisely what a dimension is and not a definition. The definition tells you the size and shape of something inside of a dimension. You can put a definition inside a dimension. You cannot put a dimension inside a definition. Which is why if you are measuring the space of something, it is inside a dimension. So when you are looking at, and you have the ability to track the generations of disintegration and then the generations of integration, and always they are equal. You're always going to have the same amount of integration or disintegration as balanced with disintegration, which is why when you assemble and deassemble, when you disassemble a radio and you put it back together, you should not have any spare parts. There are no spare parts. It means you have fucked up. So with definition, you are giving shape to it. You are defining it. And then your coordinates, your location. Now you're looking at distance. That's what you're doing when you're measuring distance. When you're measuring time. Time, you're actually measuring the integration and disintegration. And because logic has been removed from all mathematics, people are unaware that time is disintegration and integration. And as a result, we don't know that time is actually part of logic. Now, when you have the relationship, comparative relationship, that's justice. That is making sure that the equilibrium is balanced, which actually goes hand in hand with the simplification process. See, that's what's confusing me, is the ratio and the value and the relationship of something is in relative to the integration and disintegration of it. So that the integration and the disintegration is always completely perfectly balanced. So that if you have the integration or the disintegration happening over here, it's supposed to be balanced in ratio to the integration that occurs. There you go. All right, we're going to do this some more. So, what is the value of s plus 5t when s equals 3 and t equals -2? Defining the value of something. Well, define. What is the value? We're looking at definition again. Which phrase best describes the expression 3x minus 8? The number x less 3, 8 minus 3. Okay, so that's just translation. So that's translation. So we're also working on the language. So it looks like they're also working with, again, we're back to the definition. So we're looking at the language. So when you are doing mathematics, you are working among 4 different categories, but you're not told this, which is probably why you've been confused over mathematics, is because you don't know that you are working within 4 types of categories. And instead of giving the categories all to you differently and explaining anything to you, they threw them all together into a hodgepodge and said, here you go, try and figure it out. That was my problem too. I got so fucking angry. I'm like, what the fuck? Now I can tell you the purpose of this. This teaches you mental diversification because you have 4 different things happening at all times and you're constantly, you want this. But without the ability to define that you have 4 different types going on, and what they really need to be doing is label the type of mathematical problem. Are you trying to figure out simplification and integration and disintegration? Are you trying to find out definition and language? Are you looking at the coordinates and the location and the distance? Are you looking at the ratio of the comparisons for the equilibrium? These 4 things are vital in all of mathematics. You are only doing one of these 4 things over and over again. This is logic and linguistics. That's how I'm able to recognize it in mathematics. I'm like, wait a minute, we already covered this in logic and mathematics, or logic and linguistics. Why isn't it being covered here properly in mathematics? And it's because mathematicians hate words so much that they removed them all from their books. So that's exactly what it is. Yeah, this is, yeah. So basically there's a whole lot of stuff missing to make this logical, to the point where logical and linguistic people are going, this doesn't even make sense. Where's the story? They removed the story and the ordering. So we're going to put it back. Thank you so much. And may the truth always find you.